either in the audience or watching the recording of this workshop. Welcome to the 4th edition of the CTE Momentum Your Place in Space Challenge workshop. Today we are looking at space manufacturing, building for the future. And it is a continuation of Bjarke Gotfredsen's session that he delivered in our previous episode, which was all around robotics in space and robotics in microgravity. So with that, I'd like to, before I hand over to you, Bjarke, what I'd like to do is just take us through our agenda. And that is to introduce the CTE challenge and the role of MaxIQ Space. Bjarke, what I will do is that I will reintroduce you because maybe we have some people who who haven't seen last week's presentation. We'll have a Q&A session after that. We'll apply what we've learned, and then if there are any questions for the challenge team, because the deadline is coming up. So in terms of the CTE challenge, Momentum, Your Place in Space challenge, MaxIQ Space is playing the role of, we have offered to mentor, to give feedback on some of the proposals, as well as we have some prizes that are going to be awarded to either the finalists or those who actually succeed in the challenge. Bjarke Gotfredsen is one of the co-founders of MaxIQ Space. He is our technical lead and really the inventor of all of our technology. His background is very much in software engineering, but what he does is he focuses on new innovations. So with that, Bjarke, what I'd like to do is hand over to you if you would like to share your screen.
Thank you, Judy. Judy, can you just confirm that you can both see and hear this PowerPoint?
Yes, see and hear.
Okay.
Currently, it has your face in it, yes.
That's very good, thank you. So I'm gonna do it hopefully much shorter than I did last time. But this time around, it's like build in space. So we're gonna look at the building blocks that is needed in space. There's a couple of other things we have to look at first. And when we talk about building in space, of course, we can build in space for something that orbit. We can build in space, so including the International Space Station. We can build for a settlement on the moon, and we can build in a settlement on another planet such as Mars, which is probably this, when we think about building on another celestial body, is the planet we're talking about. So with that in mind, I showed this slide here last time when we ended. So this is the slide I just want to continue from. If we have to get stuff to Mars, so we just have to remember that Mars is just like a big desert. There's regolith, like sands and rocks and boulders, and there's hopefully water, and there is hardly any atmosphere on Mars. So if we have to send something to Mars that's prefabricated, and then it's going to take 115 days to 7 months if the time is right. And I'm saying 150 days because that comes out of one of the Mars programs where they have done this calculation. I'm coming into that just now. But if you have to send something to Mars that's prefabricated, such as, for example, something that generated oxygen or water or 3D built something, that is something that prefabricated. If we have to send software to Mars, which is kind of interesting because we might be sending a robot to Mars, but in order to get it to do new things, it's hopefully only going to take software. And that might only take 15 to 25 minutes. And then if we are building something on Mars, then it's going to take a few hours if we can, for example, 3D print it. So you can't necessarily set up a full-fledged factory from the beginning, but the 3D printers, a lot of people who have a 3D printer at home have their little hardware factory running, and there's actually a lot of companies that do a lot of hardware using only 3D printers as their manufacturing platform. So some of these things are important when we want to send stuff to Mars or build on Mars. We have to consider these three things. So once we go to Mars, we take one of these rockets, and I'm going to lean on the footage and the suggestion that comes out of the SpaceX Mars mission. So this is their Starship, and we just have to remember, if it takes 115 to 7 months to go there, and then we can't use, and it have to come back again, we can't use the rocket while it's in transit. So we're going to build quite a lot of rockets. So for example, at Boca Chica, they have this Starship production, and this is how it looks right now. They did like the 25th of September, so like a couple of weeks ago. And you can see there that the one they want to launch here, hopefully this one's ship number 25, which is the first one. And then they have a number of different ships that's more or less ready to go. Once they want to get it into space, they're going to use a booster. And they're also building a number of boosters. But in reality, once we go to Mars, a booster is going to be used for like an hour. And the spaceship is going to, because it's just going to send it out of this Earth's atmosphere, they're going to take 10 minutes or something like that and coming back in. And maybe it have to be refueled and things like that. But the spaceship, the Starship, that's going to be gone for like over a year, if you're really lucky, sooner. So 1 hour versus a year is the difference between why we have to have a lot of Starships and not necessarily a lot of boosters. So one of the things that comes out of that program was they had an aim in this SpaceX Mars mission to send 1 million people to Mars using 1,000 Starships sent during the Mars launch window. So the proposed journeys would require 80 to 150 days. That's what their calculators are, average 150 days. You can see that's where I get it from, over 9 synodic periods over a 17 years span. So that's kind of like the goal, and that's what SpaceX with their Mars mission is attempting to do. So we have to consider, sending stuff to Mars. When we have to send building blocks there, then what are we going to send, and when can we send it, and how much can it weigh, and things like that. The Starship originally was scheduled to be able to take 100 tons into orbit, or even further, and I think they're slowly, with the new rocket engines, being able to move that to 150 tons. And in comparison to, for example, when we went to the moon, we were talking about a few kilos. So there's a big difference. But still, 100 ton, even though it sounds like a lot, it's quite a little amount of material when we're so far away from home. So the first building blocks I want to talk about, and I think Judy talked about it in one of the early episodes, I'm not going to spend too much on it, is this MOXIE here that's going to generate air. As it says in the NASA material, makes oxygen out of thin air. So the amount of oxygen in the Mars atmosphere is 0.13% versus the 21% we have on our atmosphere. So if we had like a we had a small crew, we need like 25 to 30 tons of oxygen, similar to a tractor trailer of oxygen. And if we have to produce it on Mars, then we have to have a oxygen that's big enough, and it needs a power plant of 20 to 30 kilowatt hour. So like kilowatts to produce this thing here. So that's just one of the big things that we have to set up, is not only the MOXIE, but of course also a power plant for that. Another thing, and we're going down the line of remember from our last week, the different things that human needs is water. And there you're working on something that's called a water vapor absorption reactor. So in the atmosphere, I'm not talking about in the ground, but in the atmosphere, in Martian atmosphere, there's 1 to 2 cubic kilometers of water. And that's like 2,000 billion liters, if you like it in that number instead. But 1 to 2 cubic kilometers, the Lake Tahoe, which some people maybe know, is 151 cubic kilometers in water contents. But remember, comparing to water in the atmosphere versus a lake here, where it's, of course, condensed already. And there is hopefully also water otherwise on Mars. But in the beginning, we're going to use the MOXIE here because that is, we already established there's that water contents in the air. So we start with that. So once we have that, we have some of the stuff that we need. Then one of the next things we definitely need is shelter. So we want to print the housing there. We want to use the regolith, the soil there is on Mars, with some binding material, and then we're going to 3D print the house. So we, of course, testing all this thing here on Earth first and see if we can do it. And then once we kind of like have figured out that we can do that, we're probably going to take some prefab 3D printers and send to Mars. And then they're going to take the Martian soil plus some binding material, and they're going to then 3D print some housing. So we don't have to take that with us. And of course, once they can 3D print one of these things, they can hopefully 3D print other constructions that we might need also. And down the line with that, we actually are preparing for what we want to build and whatever other people want to build that have to go to Mars. This Mars, even though that it doesn't have an atmosphere like we have here, and it doesn't have a forest or lakes and a temperature like ours, there's a lot of this stuff where we can start training and simulating some of it here. So when we want to build something for Mars, or for Moon for that matter, then let's build it for here on Earth first. And if it's something we can actually benefit from, such as solar panels, then the sun only shines. The efficiency on Mars is like half of the efficiency here on Earth, simply because that planet, Mars, is the fourth planet from the sun, versus we the third. So we have be a bit closer and have a bit more sun on our planet. So, but that's just a matter of more solar panels. And of course, like here, it doesn't shine in the nighttime, so we need battery storage. And both of these things are produced already, and we're testing them here, and we can use them to calculate and get the price down to a decent amount of so we can, when we send it to Mars, we can send a lot of this thing to Mars. This is one of those things that's difficult to build on Mars. We can't necessarily 3D print this thing here. You probably need to build it on Earth and then sending it there. The same company, Tesla, who is doing the solar panel and the battery here, they're also doing this truck here. And there's a hope that that truck could be amphibious or otherwise kind of like be made into a pressurized vehicle. But because it's electric, it can actually drive around on Mars. We might have to sit in a spacesuit in the first many versions of this car here. But if it's mass produced, it's maybe even cheap enough that we can send them to Mars instead of having very expensive style rovers. And we can drive them around here, testing the same kind of like ground that there is on Mars. And because they're electric and doesn't have combustion, they don't need the atmosphere that normal ice cars need. One of the other companies that's related to Tesla is the Boeing company, and that's also something that's been tested a lot here, because on Mars we might actually have to live underground. There's a couple of there's actually a TV show where they kind of like demonstrate not necessarily a Boeing machine, but try to find fissure in the Mars that they can actually lower their shelter to be sheltered from the radiation that hits Mars. And if we can't actually figure out to shelter us well enough, we might actually have to then drill to be away, even if it's like, for example, for transportation purpose or something like that. So that was that drill here. So what I want to do is I want to summarize this thing here, and I'm going to use a blueprint from National Geographic here, where they kind of like show in what order they see how things are going to be done here. So cargo is coming to Mars. The first thing we're building is a hub, and then a communication satellite. We're sending a rover there. We keep sending more cargo there. Then the MOXIE I described, we have to get that to Mars, the wafer. And then, of course, that needs a lot of power. So we're going to do solar panels. We're going to do a reactor probably also. And then with that, we can then install the MOXIE and the wafer. And we're going to have a 3D printers. We're going to have workshop. And only then, when we have all those things here, we actually, at that point, only going to land people on Mars. So that's kind of like the idea, is that there's a lot of stuff that's being sent to Mars first and configured and set up and things like that, either with the robotics, or maybe we have to send a very small team that actually just go there to plug things in, but they are more or less ready otherwise. So this thing here with a building block, and we talk about something that's prefabricated, something that's software that we can load there, and of course then what can we build on Mars? And we have to build building blocks that is something that we can take to the Mars before we actually know how we're going to use it. And I'm going to just demonstrate here an example of that, because this is actually, Judy mentioned some prizes. So we have developed these small circuit boards, which is, this is in this case 2 different sensors, and you can then just click them together, and you now created a solution. You don't have to have any factory material or anything like that to put it together. So here I have an example of a circuit I built like this, and that can be put together in many different ways. This is just a very specific way. You will see now I have screwed that into a 3D frame, and there's like a battery module and a computer module and a couple of sensors. And that's I put into this cylinder here, so you can see it's screwed in here. This is all 3D printed. And with that, I now demonstrate the mechanical part and electronic part. And you can imagine you can put that together on other 3D printed things. So in this case here, I'm actually building a rocket. So this is like, there's a rocket engine, a model rocket, not necessarily a full-flown one. But whatever you want to put to Mars, you have to consider that you have stuff here where you don't really know what's going to end up. So you 3D print some of it. You can't 3D print electronics, so you have a number of different electronics components that you take with you, where you don't need, when you put it together, you don't need like a solder station or pick and place machine or anything that requires, for example, a clean room or any of that kind of stuff. You want something that you can just put together. So that's kind of like my presentation here. It's hopefully shorter, because I think I ran very much over time last time. And I was kind of like, I tried to be within my 20 minutes this time around, and I think I beat it with a few seconds here. So thank you very much.
Great. Bjarke, thank you very much. And it certainly does follow on from the previous workshop. You were able to establish a lot of context in the previous workshop. So thank you very much for that. We don't have any questions in the chat. Rebecca and Mesa, I can see that you are there. I'm just wondering if you have any questions for Bjarke before we close.
Yes. Thank you so much, Bjarke, for walking us through all of this. It's so interesting. I would love to hear you talk a little bit about what challenges are introduced by an environment that has different gravity from Earth when you're like 3D printing on Mars or the moon, or even if there's 3D printing on the ISS, like sort of what are the problems that introduces, and how might we be solving those in our development here on Earth?
Bjarke, sorry, before you answer
okay.
that, if you don't mind, just if you wouldn't mind, stop sharing your screen, because we're getting a bit of a delay on your video. Thank
That's
you.
very good.
That's
okay.
Thank you.
Thank you. So we most of us who's not in the 3D printing world, and I'm one of them. I do have a 3D printer. You can see behind me is the different filament hanging. But this is a kind of like traditional 3D printing where we have a filament and we print it and we need the gravity. Another typical one is using resin, and that's kind of like in a resin bars where we drag it out the bars, but it still needs a gravity. There's other 3D printing methods that they use in big industries, where they, I think I can remember the word, centralize the material. So it's kind of like a block of dust that you can, metal dust or whatever material it is, and then you actually send laser into the middle of this thing here, and then when you're finished, you actually just, you know, polish the dust away. And I think some of these methods here, they don't need gravity. They can actually operate in without the gravity. So on the International Space Station, I'm not sure if they have actually done any 3D printing, because some of these 3D printing facilities I'm talking about here, they're quite big. You know, there was one we have at home that need gravity that, you know, we can have in like a cubic foot of space, and that's probably what we can afford on the International Space Station. Luckily on Mars, that's one of the things there's a lot of is space, so there is not too with this. See, you know, things tend to go in the direction of gravity, so we don't need for construction or anything like that, we don't need a lot of gravity. Gravity's biggest problem is human being or animals or maybe even plants or things like that, because we as a living organism, we alter our composition to the environment we're in, and some of it we alter it much faster. I saw a clip of an astronaut that was in space for like 370 days, and he was I don't even think he could sit up. He was like carried out of the spacecraft when it landed, and that's from being in, of course, zero gravity, or what they call microgravity on ISS. And the thing is that if we go to Mars, as I mentioned last time, then the gravity will have an impact on us as humans. But from a building perspective, it's not a problem. The thing that's maybe one can kind of like consider is that when we build stuff, if we can imagine we build a high riser here on Earth, we know how much pressure there is on that building because of the weight, which is the gravity. And of course, the same construction we put on Mars can be done much lighter and easier because it only weighs 40%. So we don't have to have the same kind of like construction methods like we have on Mars. There was another thing I learned since I talked about this yesterday, was like, you know, we sometimes have an idea about how Mars is from popular movies like I had from last time, such as The Martian. And I saw this clip here with Neil deGrasse Tyson, who said this thing here about this storm on Mars that we saw in The Martian. That's not happening. And he was actually an advisor on the movie. And I said, listen, we have to have something. And the reason why a storm on Mars is not like really a big thing is because the atmosphere on Mars is 600 Pascal versus 100,000 Pascal on Earth. Okay, so it's like not even a percent. It's like 0.06% or something. It's a very, very, very thin atmosphere. So when that blows, it doesn't really matter. We can see it, but it's not like and sand will fly over and it will cover solar panels and things like that. But it's not like it will tilt a spaceship or anything like that. So number of the things we consider when we construct on Mars, that we have less of a gravity and there's less of an impact from a storm and things like that, is more like a benefit than it's something that counts against us. And one of the reasons, for example, we also do the International Space Station, because a lot of the stuff we do on the International Space Station, stuff we can only do when there's no gravity. There's like, I think there's a certain thing that they grow and try and things like that, where there's a couple of other companies, I think Nanorex or a couple of other, they're busy putting up robotics space stations. So they're not operated by people, but they send up robots and it offloads stuff, and then it gets produced as like a factory in space, and it gets offloaded and come back to Earth. Because producing it in zero gravity is just make it much more easier to produce certain things. So we can also look at it as a benefit. So I don't think that the gravity, or for that matter, the weather I was talking about last time, is that bad. What is bad is like the lack of pressure. But again, that is also more like a thing for humans. We need the pressure. So when we have the 1 atmosphere pressure that we need, and we have to have it so we can breathe the air and all that kind of stuff. Robots, 3D printers and things like that don't really care. There might have to be done something special for these 3D printers to operate under, hardly any pressure. But it's not going to be a headache. Let me put it that